Hi everyone, and welcome back to the Hardware Systems Applications Past Paper lecture series. Today we will be picking up where we left off in the 2018 paper, and we will be looking specifically at section B of the paper. Okay, now as usual, just as with the 2019 paper, section B has two questions, questions 5 and 6. One related to drawing a block diagram or finite state machine transition diagram. One asking us to draw a block diagram of the system with inputs and outputs, and the other part which asks us to draw the state transition diagram for the design. Question 6 is the coding aspect of the question, where we will be asked to write the entity and architecture in VHDL for the question. We have two design options, one of which is a serial communicator. Now this is a question we have never seen before. And the other option is a variation of the traffic light question. So let's get started with option 1, and we will be answering questions 5 and 6 for option 1. Okay. Now, before realizing what the interface of the entity will look like, and before thinking about the finite state machine diagram, we need to actually understand what serial communication is and how serial communication works. Okay, so let's just read through the question once, and then I'll explain it a little bit. So the question reads, to interface with an external block, you need to design a serial communicator that takes in parallel data and sends it out serially. The timing diagram for this serial transmission is shown in figure B1. That's this diagram here, which we will look at in a little bit. Note the following specifics. The logical high level is at the bottom, whereas the top indicates logic low. All right, so note that from the timing diagram, we may think that this is logic 0 and this is logic 1, but note that the logic is inverted. In other words, a high or a logic 1 is on the lower part of the diagram, whereas a low or logic 0 is on the high part of the diagram here. Okay, so it's just inverted, and the only reason it's inverted is because they are using an active low scheme, and it kind of adds to the complexity of the question a little bit. Okay. So reading again from these notes below here, there are two start bits and a single stop bit. All right, so that is referring to these here, two start bits and a single stop bit. That's here. The address bits shown in the waveform are only an example. That's these bits here, these 4 bits. Your design should be able to deal with any address value. The data bits provided are only an example. Your design should be able to deal with any value. So what this means for us is that there is this serial communicator which is going to take in data in a parallel manner, and what that means is like 8 bits at a time. So here from the timing diagram, we see that the address bits is 4 bits wide and the data bits are 8 bits wide. Okay, so how the serial communicator works is it's going to take in the 8 bits and the 4 bits. All right, it's going to, when these start bits initiate data transmission, it is first going to communicate these 4 address bits. And what the address means is that it is going to tell the receiving end of the serial communicator that I want the data that's going to be transmitted here to be stored in some address on the receiving side. All right. So essentially, this is we're going to take in parallel data, convert it to serial data, transmit that data serially, and when we say serially, we refer to 1 bit at a time. In other words, we're not sending all 8 bits. Instead, on every clock cycle, right? And the clock cycles, of course, are denoted by these demarcations in this timeline here. Right? So what that means is that every every mark here could be considered the rising edge of the clock which governs the overall system. So on every rising clock edge, we're going to send one bit at a time to the receiving end of this serial communicator. Okay? We don't need to delve deep too much into serial communication, but all we need to know is that there's some sending end and a receiving end. On the sending end, which is the one that we are designing, we will take in data in parallel, convert it to some serial output, send that data serially across some wire or some line or something of the sort. And on the receiving end, we are going to take in that data serially and convert it back into its parallel form, and the receiving side will have access to the data. Serial communication is used in applications such as USB devices. USB actually stands for Universal Serial Bus. And as a matter of fact, fiber optic internet works on serial communication by flashes of light. When there's a flash of light along the fiber optic line, it represents a logic level 1, right? And when there's no flash of light, it represents logic level 0. Okay? Serial communication can occur in simplex mode, which is one-way communication. That's what we are designing here, i.e. from sending to receiving end. And there's also full duplex communication, which is two-way communication between sender and receiver. But we're not going to get into that level of complication. All right? So now that we have this here, let's kind of look at what this system could possibly operate as, or how this system could possibly operate. So the first thing to think about is what this system is going to look like in terms of its inputs and outputs. Okay, and the reason we would like to do that is for question 5 part A, which asks us to draw a block diagram of the full system that shows inputs, outputs, internal components and their interconnections, state any assumptions made. Okay, so we have to determine this by using our knowledge of serial communicators. And by our knowledge of serial communicators, I mean we're just going to think about what I just talked about. And we are going to look at the timing diagram here to help us figure that out some more. Okay? So what I'll do is I will pull up a Jamboard here, and we can think about this a little bit. So from the diagram, we see that there is going to be some series of bits that will be sent as output. So this diagram here actually tells us what is the output of the system to the communication link that is going to be received on the receiving end of the system, or the serial communicator. Okay, all right. So what it tells us here is that we are designing a serial communicator that takes in parallel data and sends it out serially. Okay, so what is meant by taking in parallel data? Well, that actually means taking in a group of bits at the same time, kind of like a standard logic vector. Looking at the diagram now, we know that we have a set of address bits that will be sent in serially, and we have a set of data bits. Sorry, the address bits will be sent in parallel, and we have a set of data bits that will be input into this serial communicator also in parallel. In other words, 8 bits at a time. Okay, so we could think of that something like this. So this is going to be question 5, part A, right? And we're going to have this system here. Now, we know for sure that we will have a clock, all right, so let's just put in our clock and reset one time, because these are sequential devices. Okay, once we're designing for using a finite state machine, and once we're designing devices like this, they're going to have a clock and a reset. Okay, we're definitely going to have our data in, all right, and that is going to be 8 bits wide, so we could denote that like this. We are going to have our address bits, and from the diagram we know that the address bits are 4 bits in width, so that's going to be 3 to 0. All right, and the last thing that we would need as an input is a start communication bit. All right, and this is going to allow us to start the entire process of sending these bits from inputs to outputs. Now, this start communication bit is not the same as these start bits here. Okay, the start communication bit is a state, is a bit that takes us out of this waiting state and into some state that is going to accept these start bits. So don't think of that start communication signal as the start bits from the diagram. Okay, so what I'll call that is I'll call that start com or start communication. Okay, the next thing we know from the diagram is that these bits are sent out serially, right? That's what we have underlined up here. It says that it takes in that data in parallel and it sends it out serially. What is meant by serially? Well, that means 1 bit at a time. Okay, so our output, we will now call our data out. You could call it serial out, anything of the sort. And it is a 1-bit value, okay? Like a standard logic, a single standard logic bit. Okay, and that basically brings us to the end of question 5 part A. So this is what the entity is going to look like. It is going to have a clock and a reset as input, an 8-bit wide data signal, an 4-bit wide address signal, a start communication signal, and a data out output, which is going to send those bits serially across the transmission medium. Okay, so some assumptions that we could make in this. All right, and our assumptions are always based on the particular situation. Okay, so we know for sure that we could say, well, I'm not going to say assume that for everything because I'll just have to rewrite that over and over. So our first assumption would be data is sent in parallel. And I know that they tell us that in the exam paper, but serial communication questions, and there are quite a few of them, they may not always tell you that. So I'll just list that as an assumption here, right? So data is sent in parallel. Right? Or rather, I'll say data is input in parallel instead of having sent in. Okay, so data is input in parallel and sent out serially 1 bit at a time. Great. A next assumption, which we will typically have for any question in this section, would be assume that, let me stop saying assume that, the reset signal is active high. And of course, you could say it's active low if that is what your design will be assuming. Just ensure that you do design for active low if you state that it is active low here. If it's active low, of course, you're going to be looking for if reset is equal to 0. I personally like to have asynchronous resets. So I will say that in my design, my reset is asynchronous. Remember, the asynchronous reset takes priority and is not takes priority over the clock and is not governed by the clock. So it's a separate if statement outside of checking the clock edge. Whereas if it is synchronous, it will be dictated by the clock and will be a nested if statement inside of the check for a rising edge of the clock. Okay, the last thing I want to cover is the start communication bit here. Okay, so our third assumption will be that there is a start communication bit and that is essentially going to take us out of the waiting state. Okay, that will denote the start of serial transmission. Right, I remember both the start, everything is being sent serially. The start bits, the address bits, the data bits, and the stop bit. Each of those things are sent serially one by one over that data outline. Okay, so denote the start of serial communication. And allows the system to exit the waiting state. And we'll see that how that works when we start implementation and when we're looking at the finite state machine diagram. Okay, all right, and that takes care of our diagram and our assumptions for question 5, part A. Okay, part B now asks us to draw the state transition diagram and to state any assumptions. So we are going to figure out the states from this timing diagram here. Okay, there are some more details in this diagram that we will need to pay attention to, but we'll get to that when we start the programming. Okay, so let's go on to another page. All right, now this timing diagram tells us that we have a waiting state in which the serial communicator is dormant. We have a start state, which that start communication bit is going to take us out of this waiting state and into the start state. And when we are in the start state, we expect to send 2 zeros. All right, note that this is 2 clock cycles, and because it is 0, 0 here in the diagram, or this high edge here, we know that that corresponds with a logic level 0. Okay, so if I'm in the waiting state, I'm constantly in this dormant waiting state and no data is being input. I press some button that probably triggers a start communication signal, and the first thing that's going to be input into my system is, or rather the first thing that's going to be sent out of my system is, along the data outline, is these 2 start bits as 0, 0. Then I will send out whatever is in the address bits. Okay, so when I'm in the waiting state, so let's just say we have some state called waiting. All right, so let's list our states here. So we have the waiting state, we have the start state, right? We also have a state in which we will communicate the address bits that are on the address line in this diagram here. Okay, all right. After we send the address bits, we are going to send the data bits. So that means that we're going to have some state for transmitting the data, and we could call that the data state. All right, in other words, everything that's on this line data in is going to be sent out across the data out state. Okay, and then after we send this data, this is the data state here. After we send out this data, we're going to send a stop bit to tell the receiving end that we have stopped communication, and that will lead us with a stop state for this communicator. All right. Okay. So these are our states, and we could actually start drawing the state transition diagram now. So I will let my wait state be my initial state. So because it's the initial state, I'm going to denote it like this. I'm just going to put the words reset here. All right. Out of this waiting state, I'm going to go into the start state. What is the input to the system that allows me to transition from this waiting state into this start state here? So let me just draw a state bubble for start. Right? So we could say in our design, when start com is equal to 1, that's when I'm going to transition here. So we state that input into the system by writing along the transition here, start com is equal to 1. Okay. How do we go from the start state into the address state? Well, that means that 2 clock cycles would have passed. And how do we typically keep track of the clock cycles? From the previous questions that we looked at in this section, we typically use a counter, and that counter is going to increment on every rising edge. Okay, so I could say when the count value is equal to 2, assuming that the count starts at 0 when I'm in the start state, I am going to transition out of the start state into the address state when the count value is equal to 2. So I start at 0 and I say 0, 1, 2. Right? Going from 0 to 1 is 1 clock cycle. Going from 1 to 2 is another clock cycle. So I'm going to transition into my address state when the value of count is equal to 2. But I need to check when count is equal to 1, and I need to increment the counter. All right? We know how we do that counting increment by allowing this to transition back to itself. And here we're going to increment the counter in this state. So count is equal to count plus 1. Okay? Using that same logic of checking how many clock cycles have passed, we need to count when these 4 bits are sent out before actually sending out my data, right? And to do that, we see that these are 4 clock cycles here. So again, I could just check the counter here, right? And going from here to here, I'm going to say count is equal to count plus 1. Right? Let me see if I could take this from here instead of having to rewrite it. I guess I can't. I thought I could have copied it. So let me just rewrite here. Count is equal to count plus 1. Now we're using the same counter, and we would like to check when 4 more clock cycles have elapsed. Coming into the address state, our count value is 2. So we want to see when count is equal to 2 plus 4. So the condition that's going to allow us to transition out of this state is when count is equal to 6. And of course, from the address state, we are going to transition into that data sending state. Okay, so we will denote that as our data state. All right. And again, we want to check when 8 bits have been transmitted. So to count those 8 bits, we're going to have this self transition saying count is equal to count plus 1. And then we're going to exit this state when the count is equal to 8. And after this data state, we will like to go into the stop state here. All right, where we will just be sending 1 bit at a time. Well, just 1 bit, and that's 1, 1. Remember, it's a logic level 1 that we're sending there. Okay, so going from my data state now, I will be going into my, let me just draw it here. Draw this as the stop state. Right, and from the stop state, I'm going to go back into that dormant state by incrementing the counter once. And then checking to see when the counter has a value of 9. All right, pretty straightforward stuff there. Okay, let me just make sure, sorry, not 9. We don't want to check when count is equal to 8. We want to check when count is equal to 8 plus 6, which is 14, sorry. In other words, 8 more bits have passed. And then when 1 more bit has passed, we want to check when count is equal to 15. So our counter is going to be some integer value that ranges from 0 to 15. All right. Okay, and that basically takes care of the state diagram for this question. All right. We will be looking at a couple more serial communication questions to kind of ensure that we are prepared for this. But that basically takes care of question 5 part B for 15 marks. All right. So now we can go into the coding part of this question. Okay. The question reads, for question 6, design the system for part B. Question 5, with the aim to program it into an FPGA by using appropriate software toolchain. Include comments in your code to explain the operation of your program. Each block of code should have a comment section explaining the purpose of that block of code. Same applies to important lines of code. So we are required for 4 marks to write the entity. Of course, the entity will correspond to our diagram from question 5 part A. And our architecture is going to emulate our state machine diagram or our state transition diagram for 16 marks. Now, for the purpose of the online exam for the 2020 examination, we will not be doing this coding, or we would not be needing to write this code in quarters 2. We would actually have to write this on paper. However, for the purposes of this video, I will be actually coding this out in quarters. Okay? So it's important that we know how to write out this code and what exactly we are expected to produce for the exam for this same 20 marks. Okay? All right, so I'm going to start a new project here. I'm going to call this the 2018 past paper. Okay. Again, this really doesn't matter at this point in time, right? Okay, and let me add a VHDL file to this project. All right, as usual, we're going to be doing our package declaration up here. Now, the question asks us to write comments, which means that to explain each block of code when you're actually writing this by hand, you're probably going to have to include comments. Include those comments using these two hyphens wherever necessary. Okay? Question 6, part A. We have the entity, we'll call this serial communicator. Right, it's important that we know the syntax and where semicolons go and all that when we're actually writing this by hand. So it's good for us to get practice for this. Okay, so I'm going to call this serial communicator.phd. That's probably going to cause a problem with the top level entity, so let me just set this here. All right, so our input ports will be our clock, our reset. Of course, these are type standard underscore logic. Right, so we have our clock and our reset. We're going to have data, address, and startcom bits. Data and address are standard logic vectors. Startcom is a single bit. Okay, so let me put in startcom first. These are inputs. Okay, now this is a standard logic vector of some 4-bit width. Okay, now for us to figure out this width, we're going to look at the timing diagram here now. This is pretty important, so we might want to pay attention to this. Now we know that it's 4 bits wide because each bit is sent out on a clock cycle, and it takes 4 clock cycles for this to send out the entire address on our data outline. However, if we pay attention to the difference between the address and the data vectors, we'd see that the address sends out the most significant bit first, followed by the least significant bit last. Whereas our data sends out the least significant bit here, followed by the most significant bit here. All right? That will actually dictate how we write or how we declare the size of the vector, whether we use 0 to 3 or 3 down to 0, and whether we use 0 to 7 or 7 down to 0. All right, and just looking at some of the other past papers which have these questions, the 2016 paper also has some serial communication in there. However, there aren't any address bits here. However, we still need to pay attention to this least significant bit and most significant bit thing. All right, the 2014 paper likewise has some address bits here. However, actually, it's the same thing. So our most significant bit to least significant bit, then our least significant bit to most significant bit. What is meant again by least and most significant bits? Well, remember, right, I could actually draw it on this page here. If I have a value like this, right, let's just say address is 1001. This is always our most significant bit. This is always our least significant bit. Okay? However, if I say that this is address 0 to 3, that implies that I'm indexing this vector using indices 0, 1, 2, and 3. Okay, let me just change this to 1011. If I was using the same address, 1011, but I was declaring the vector as address 3 down to 0, then what that means is that this would, while this is still the most significant bit in the data string, or in the bit string, and this is still the least significant bit, that the indices change to this being 3, 2, 1, 0. All right, so let's see how this differs. Well, in this case here, address 0 refers to this bit. Address 1, right, so that's that first one there. Address 1 refers to this bit here, right, because this is how we index that vector. Address 2 refers to this bit here, and address 3 refers to our least significant bit here. All right, so let me just neaten this up a little bit, make this right. So this is address 0, this is address 1, this is address 2, and this last bit here is address 3. Okay, so we have address 0, address 1, address 2, and address 3. However, the significance of the bits does not change. The only thing that changes is the indexing. So this is still my most significant bit. This is still my least significant bit. The same thing occurs in this indexing scheme here. All right, so address 3 is now going to be this one. Address 2 will be here. Address 1 will be here. Address 0 will be here. However, this is still my most significant bit. This is still my least significant bit. In other words, address 3 in the second scheme will yield the most significant bit, whereas address 3 in the first scheme will yield my least significant bit. Now that is important for us because we need to know which of these bits we're sending out first. So if we would like, so how we're going to do this is on every rising edge, we are going to increment the counter, as we know. And this counter is actually going to be used as the index to index these bits here. So if we would like to send out most significant bit, least significant bit, most significant bit, then a lesser, then a lesser, then a lesser, which is what we're sending out here. Then as the count value increments, we want this to be the most significant, then this, then this, then this. In other words, our indices are incrementing in value, which means that we would need to declare this vector as size 0 to 3. The data input follows a similar train of thought, in that I would like to send out the least significant bit first, up until the most significant bit. However, remember the least significant bit is always the rightmost one. but I'm still using the counter that is constantly incrementing to index that 8-bit wide data vector. So as the counter increments, I would like to start with the least significant bit and send out more significant bits as I go along. Therefore, this would need to be a value of size 7 down to 0. And then finally, the last thing that I'm sending out here is my data out, which is an output that is 1 bit in length. This may be a little bit confusing at first, but when we write out the rest of the program, we will see exactly where that 0 to 3 and 7 down to 0 comes into play in terms of the significance of bits. Okay, so let's move on now to part B of the question. All right, so part B asks us to write the architecture for 16 marks. And of course, the architecture is where we're going to have all our process blocks and all those things. So, yeah, let's just start off here. All right, and our architecture is going to have a begin and an end section. Right. Now, in this part here is where I would like to first of all define the data type for the states. Okay, remember we do that using this here. Say type state is, and I list the states that I'm going to have in here. Now, my states, as we know, are the waiting state, the start state, address state, data state, and stop state. All right. Now, I can't call the state wait because we know wait is a special keyword in VHDL. So I'm going to call it waiting. I'm going to call it the start state, the address state, the data state, the stop state. All right. So 5 states corresponding to each of my state bubbles here. 1, 2, 3, 4, and 5. All right. Next thing I would like to do was to declare signals to hold current and next states. Right, these are of type state, a type which was defined above. Right, and then I would like to declare signal for counter. My counter is going to be an integer that will exist in the range of 0 to 15 as determined by our state diagram. Right, and that takes care of this signal declaration system in our architecture. The next thing that I would like to go on to is the actual body of the architecture. Now, before we start writing the processes, let's just take note of what are the processes that are required. Right? We're going to have our process to determine what is the next state in line, which we call that our next state logic process. We're going to have a process that is going to take care of the actual transition of states from current state to next state based on the logic determined in this first process here. All right. We are going to have our counter process, which is going to essentially increment that counter on every rising clock edge. And we're going to be using that counter to determine when to send outputs. And finally, speaking of sending outputs, we are going to have our output process here. And these are typically the 4 processes that we would like to have in any of these questions here. All right, any question for section B would be would contain these 4 processes at a minimum. All right, so I'm first going to write the process for our next state logic. All right, if you want, you could say this process determines the logic of the next state based on the input of the current state, or rather it actually determines the next state based on the input of the current state, based on the input and the current state. Okay, so we're going to call this next state logic process, and it is going to be dependent on our start communication signal, because now we want to have something to wake up this process when I want to come out of my waiting state. It of course is going to be dependent on the reset signal, the counter, and it's going to be dependent on how the current state changes, because every time the current state changes, you always want to evaluate the logic for the next state. Okay, as a matter of fact, the reset signal is not necessary here. It will be necessary in the other process. So I'm just going to write my begin and end keywords for this process, and we can begin. So remember, in this next state logic process, the first thing that you always want to do is assign next state the value of current state. And again, the purpose of this is if current state changes in another process, however, it's not time for us to move on to our next process, to move on to our next state, sorry. It's not time for us to move on to our next state. Then the second process, which takes care of the transition and always assigns the current state to the value of next state. If we don't want to transition, then we will just allow the current state to stay within itself. Okay, so this is a very important line, and it's always necessary. The next thing we want to have is our case when statement. So in the case of when the current state is, then we're going to have a bunch of whens here. Okay, so when my current state is in the waiting state, well, what do we want to do? We want to look to see if startcom is equal to 1. So if startcom is equal to 1, that is when I want to transition out of the waiting state, and I'm going to go into the start state and wait for those two start bits to be sent out on my data out. All right, when I'm in the start state, well, remember, I'm going to transition to the next state when my count value is equal to 2. All right, I don't need to increment the counter here. That's what the counter process is for. I just need to check the value of the counter. So if counter is equal to 2, right, note that this is an integer, so we don't need single quotes around it. Okay, then my next state is going to be my address state here. Okay, of course, in the address state as well, I'm going to increment the counter, but I want to transition to the next state when the counter is equal to 6. All right. So when the current state is address, or when I'm in the address state, well, if my counter is equal to 6, then I want to transition to the data sending state. When I'm in the data state, then remember my counter needs to count 8 times to signify that on every rising clock edge of the clock, a bit has been transmitted in the parallel data from the parallel data input. So after 8 clock cycles have passed, the counter would have incremented to 14, right? Because 6 plus 8 is equal to 14. So if the counter is equal to 14, then the next state I'm going to go into is my stop state. All right. And then finally, when I'm in the stop state, we only want to transmit one stop bit, which means that we have to check when one further clock cycle has passed, and we of course checking these clock cycles based on the value of the counter. So if the count is equal to 15, then I'm gonna go back into my waiting state and wait for start count to go high again. Of course, for the case when statement, I must have a default case, and your default case always allows you to go back to your initial state, which in our case is the waiting state. And that takes care of this process. Okay, the next process that we would like to write code for is the state transition process. So just writing a comment here, state transition process. This process executes the change of states depending on the logic determined in next state logic as the process from above. Okay, so I'm going to give this state the name state transition. Remember, of course, these processes are all concurrent to one another. Okay, this process now is going to be sensitive to rising clock edges and my reset signal. Why? Because I want to check when I'm at the edge of when I'm at the rising edge of a clock. That's when I want my state transitions to occur, and when my reset signal is high, I want to go to my initial state corresponding to this reset here. Okay, so remember we said that we have an asynchronous active high reset. So the first thing I want to check to see is if my reset is equal to 1, then my current state signal is going to be assigned my initial state. Then I'm going to check to see if I'm at a rising clock edge. Then my current state is equal to my next state. Now this process has no notion of what the next state is going to be based on the current state. That is assigned here, right? So if the next state is assigned here, all this is doing is every rising clock edge, whatever is the value in next state found in this previous process is going to be assigned here. What that means is that for some rising clock edges, for example, in the address state or the data state, I'm going to have a rising clock edge here, here, here. However, I'm not changing state from the address state. Okay, I'm only changing from the address state when 4 clock cycles have passed. That is why we have this line on top here. All right. For example, if I'm in the address state and the counter is not yet 6, then I don't want to tell next state to be equal to data, but I still have to give the signal next data value. So I'm going to give next state the value of whatever is the current state, which is going to allow me to stay in this address state until the counter value is equal to 6, which is the significance of this line of code here. All right, because if we don't have that, current state will change to some other wrong thing, and we would probably change states when we don't want to change states. Instead, we want to stay in that state. All right, but that takes care of this state transition process. All it is that we're checking the reset signal. If the reset is high or low, depending on if it's active high or active low, we go into the initial state. Then on every rising clock edge, current state is equal to next state. That is it. We end off this process. And that's it. That takes care of our second process. Remember, we have 4 processes in total. The next process we're going to look at is the counter process. And remember, all that process does is it is going to increment the counter on the rising edge of a clock. So this process increments the counter on the rising clock edges. This counter is used to count the number of clock cycles that have elapsed and allows us to index the data and address parallel inputs. Remember, parallel input is always a standard logic vector. We need to index those. Okay? All right. So I'm going to call this count proc, and this is a process that is sensitive to changes in the current state as well as the clock. Remember, it needs to be sensitive to the clock because on every rising clock edge we want to increment that counter. Okay, so what's going to happen inside here now? Well, first of all, let's take care of these rising edges. So if my clock event and clock equal 1, in other words, if I'm at the rising edge of a clock, then, well, let me put this end if here first. All right. Well, what's going to happen? When do I want to increment this counter? I don't want to increment the counter in the waiting state. I want to increment it in my start state, in my address state, in my data state, and in my stop state. How do I know I want to increment it in those states? Well, that corresponds to these counts increments here. All right? So that's the only time I want to monitor that counter or allow that counter to increment. So the first thing I need to do is check to see what state I'm in. All right? Because we're reading current state in this process, that's why it's in the sensitivity list. So if the current state is equal to the waiting state, then I'm going to reset my count value to 0, because remember, the counter goes from 0 to 15, and the only time the counter, we don't want to start counting here, but once we reach in this starting state, we want to let the counter start off at 0 because we check in these particular values of 2, 6, 14, 15, etc. So whenever in the start state, we want this counter to start counting at 0, and we could set that in this waiting state here. Okay, so if I'm in the waiting state, then my count value is equal to 0. Else, if I'm in any other state, in other words, if my current state is the start state, right, or if my current state is the address state, or if my current state is the data state, remember these are all the states we want to count in, right? Or if my current state is the stop state, right? Then, well, that's when we want the counter to increment. Is it count or counter? The name of the signal is counter. Okay, so here we want counter to be equal to 0. Counter is equal to counter plus 1. All right, and that takes care of this counter process here. All right, now on to our fourth process, which is the output process. And of course, our output process determines how this waveform here, of course, this is just an example waveform, but how something looking like this waveform here is going to transmit that data on that data output line here. Okay, so let's go back to this here. All right, when I'm in the start state, I only want to transmit zeros. Seeing that there? I want to transmit 2 zeros. I don't need to count the zeros in this output process because the counter is taking care of that for me. Right? How do I know when I'm sending out zeros for 2 clock cycles? Well, this is taking care of that for me, and the counter is taking care of that for me. So all I need to do here in this process right, let me just set things up here. This is going to be sensitive to the current state, right? It is going to be sensitive to my data input because that's what I am reading in, right? Okay, so just saw a little error here. I can't name this input data because that's the name of the state here, so I'll change this to data underscore in. All right, so what that means is that this process is going to be sensitive to my data input. sensitive to my address input. Right, my input is called address, the state is ADER. So I'm gonna let this be sensitive to address, the actual input itself. All right, and of course it's gonna be sensitive to my counter. All right. What does this mean now? Well, when the current state is in the waiting state, or when it's in the stop state, notice that I am transmitting a logic level 1. Okay? All right. So here I'm going to say if the current state is equal to waiting, or if the current state is equal to stop, then I want data out to be sending out 1s. All right. When I'm in the start state, I'm sending out logic level 0s. Right? So when current state is equal to the start state, then my data outline is going to be sending out 0s. Again, we don't need to count the number of zeros in this process to see if I'm sending out 2 zeros, because I'm going to exist in the start state for 2 clock cycles. Those 2 clock cycles we know are going to last for 2 clock cycles from the counter process. And as long as I send out a 0 in that start state, because the other process ensures that I'm in the start state for 2 clock cycles, I'm going to send out 2 zeros. Right? Then, if I'm in the address state now, what's going to happen? Well, if my current state is equal to address, then data out, which is that thing that's sending out data 1 bit at a time, is going to be sending out the different parts of this address signal here. So firstly, we know that if we want to send out the most significant bit first, we want to send out this one here. So we have to send out address 0, then we have to send out address 1, then we have to send out address 2, then we have to send out address 3. All right? I have a counter which is counting using integers. So I can say, let me now index this address input here to get address 0, address 1, address 2, and address 3 using the counter. All right? But when I am in this address state here, when I've entered this address state, the count value is already 2. What that means is that in this address state, the count value is going to be 3, 4, 5, and 6. But I don't have indices in my address vector called address 3, address 4, address 5, and address 6. Instead, what I'm going to do is I'm going to say, let me address this vector address 0 to 3, right? Remember, this is of size 0 to 3 here, okay? Using this integer here, this integer value called counter minus 2. When I'm in the address state, my counter is equal to 2. All right, let's just work out some of this logic here. My counter is equal to 2. Therefore, address counter minus 2 is the same as me saying address 2 minus 2, which is address 0. All right, and remember, address 0 is going to be our most significant bit, because we declared this port to be of the vector width 0 to 3. Therefore, address 0 gives me my most significant bit. And that is where the significance, the whole thought, or the whole concept of 0 to 3 versus 7 down to 0 comes into play. Because I want to send out the most significant bit first. Alright? So I am going to index this address port vector, or the standard logic vector, using this number counter minus 2. Now when counter is equal to 3, right, I'm going to index this thing using counter minus 2, which is now going to be 3 minus 2, which is now going to be address 1, which is going to give me this bit here, my next most significant bit, right, or the lesser significant bit. All right, and that's why we use that indexing scheme there, and that is the significance of using the vector, declaring the vector using 0 to 3. That same logic applies when I'm in the data state here now. So if my current state is equal to data, then my data out, which I'm sending out 1 bit at a time, and I'm sending it out 1 bit at a time from this 8-bit wide data parallel input there, right? I want to send out least significant bit to most significant bit. So how does that come into play now? Well, let's go back to this Jamboard here. Okay, so let's just say my data looks something like this, right? Right? I have this as my most significant bit. I have this as my least significant bit. Now on the data outline, I would like to transmit this bit first, then this bit second, then this bit here, then this bit here, etc., etc., etc. So I want to transmit these bits from least significant to most significant in that order, right? Because that's what the timing diagram tells me here. Now, the reason we declared this as 7 down to 0 is that now, as the counter increments, so when I get into the counter state here, my count value is equal to 6, which means that the count values inside of here are going to be 7, 8, 9, 10, 11, 12, 13, and 14. So going from 7 to 14. All right. Sorry, going from 6 to 13, sorry. So that's not 7 to 14. The counter is going to be 6 when I enter this state. So my counter is going to go 6, 7, 8, all the way until 14. All right. Here now, when I'm sending out these bits, I'm going to take whatever is on the data bit, the data input, sorry, and I'm going to minus 6 from that when sending that data out on the data outline. Why am I minusing 6 now? Well, the same logic applies. Think about it. When counter is equal to 6, right? Data in counter minus 6 is going to be the same as data in 6 minus 6, which is the same as data in 0. Data in 0 from here now, because I index this thing using indices 7 down to 0, then this is now my least significant bit. All right? Okay. When counter is equal to 7, data in is being indexed with counter minus 6, which is going to give me data in 7 minus 6, which is going to give me data in 1. Data in 1 now refers to this bit here. And remember, I'm going from least significant to most significant based on this here. So that means I'm going to transmit the bit of the next, or one bit higher in significance. Then each clock cycle we go higher and higher is going to be increase in significance from least significance to most significant. All right, which is the importance of declaring this with a size of 7 down to 0, specifically declaring it using to versus down to. All right, so the takeaway from that is, if we are given a serial communication question, pay attention to this more significant or least significant. If it goes from most significant to less significant, we're going to use 0 to something. If it's least significant to most significant, we are going to use something down to 0. All right, so keep that in mind. I'm going to remove these here. And finally, we're going to check to see if our current state is in our stop state. Actually, no, we took care of the stop state above. So yeah, that basically ends off this process here. So we check to see what is the state that I'm in, and depending on the state that I'm in, I'm going to transmit some particular data on my data outline. And that brings us to the end of this piece of code for the serial communication question. Note that the 2018 paper is an exact repeat of the 2014 paper, so the solution code for this is available on the course Moodle. It has always been there. Okay, there actually is no difference between the design case study, so the code will be the same. All right, the question is asked a little differently because this requires us to draw a test bench and all that, so we're not going to be doing all that. Okay, but the code will be the same for the entity and architecture. Alternatively, you can pause this video at different parts and you can take the code down from here. I would like you all to get into the practice of writing this out and being able to write this out syntactically correct, because that is the format of the exam come next week. All right. Okay, so thank you very much for listening to this, and in another video I will be looking at the traffic light question from this paper. Thanks.